all set, and we're going to start officially. I really hope these breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing breakthroughs that we are seeing in AI. We're seeing, like, if you look at that timeline, we're seeing amazing breakthroughs, like really amazing, to the point that it's not about what technology is capable of doing. We're past that point. Technology, AI technology is so powerful that we're beyond of that question of, is technology able to do those things? We're now in the question of what technology should be doing. So not what is possible, but actually what is supposed to be doing, and how is it supposed to empower us, and how is it supposed to help us, versus the technology for the sake of technology, right? And the way that we are thinking about this is we have set up some ethical principles that you probably have read about if you read The Future Computed. These are the 6 ethical principles that Microsoft is, we are living by it. It's more than only talking about it, it's more living those principles. And this is, I'm going to do a brief introduction on these principles, but the point here is that what we are trying to share with you today is how we are bringing these principles into reality. And as I said, this is a lot of things. And it's not only about technology, it's about processes, it's about wanting to do the right things, it's about trying, it's about learning about what you are doing and what you need from us. And we have to do this with a really open mind and with a lot of humbleness, because there are a lot of questions that we don't know the answers. So, having said that, for us, the most important thing is accountability. We all are accountable of making responsible technology. Not only Microsoft, the whole technical community, the whole business community, we are all accountable of this. And this is like the foundation of everything. If we don't feel ourselves accountable, we have an issue. This is all our accountability, not only Microsoft, but everyone's. Then the second one is transparency, because you cannot trust a technology that you don't really understand how it works. So being transparent, again, is a really broad topic. We're going to talk today about intelligibility, but that's just one part of transparency. Transparency is about open sourcing things. It's about documenting things. It's about understanding how a data set behaves, right? It's a broader topic like that that we would be happy to discuss with you later. And then the other 4 that you see up there: fairness, reliability and safety, privacy and security, and inclusiveness. Those are all very important principles, and if you haven't read The Future Computed, I'd really recommend that book. I mean, it's free, so it's an easy recommendation. You don't have anything to lose by reading it, and it's a really good book. It's eye-opening. And I encourage you all to come to the booth and learn more about these principles. But having said that, today's session is not about telling you about the principles, it's about showing you how we are putting some of these principles into action. To be concrete, it's about intelligibility and privacy in AI. And I'm doing this disclaimer because I want to reinforce again that this is an incredibly broad topic, incredibly complex, that spans a lot of different things, from technology to processes to the mindset of people to culture to, it's huge. We could be days talking all over this. So come by our booth to learn more. I will be here 3 days, and I'm capable of speaking for 3 days straight. Trust me on this. So come by, and I will be happy to discuss all these things with you. And now, let's go for the specific things. One of the big challenges that we have in AI is privacy. Because let's face it, and Kim is going to be introducing this topic, but let's face it, when we are using cloud services, we are exposing our data. It can be location data, it can be health data, it can be finance data, but we are exposing our data, and we believe that that's the only way to do it. We believe that if we don't expose our data, we can't get the services. Well, actually, it turns out that we can. And Kim has been researching this kind of technology for years, so I'm not going to make my introduction longer. Thank you, Kim.
Thank you, Esther. All right. Of course, basically, everyone loves AI these days, and this is a very technical audience. We all understand the benefits, we all understand the downsides also, and the limitations of AI. And one of the key questions that is very relevant today with this technology becoming more common is who exactly will have access to my data? Well, what do I mean by this? All these machine learning technologies are data hungry, learning, and just using the model. It needs raw data, and then it can give you that prediction, that valuable prediction that you want. If you want to learn that model, you want to train that model, it requires tons and tons of raw data. And in this sense, data privacy itself is not really built into AI workflows. In fact, one could even go to the extent of saying that data privacy is often at odds with the goals of learning. The whole point of learning is that the model somehow acquires information about the training data. Well, again, since this is such a technical audience, maybe this is very obvious to many of you. Let me just mention a few special examples that I really like. Health data privacy is super, super critical. If I'm hoping to use some kind of health predictive model and I'm going to send my data somewhere to be predicted on, I certainly have a lot of questions about how my data is handled. Same for financial data. What about calendar data? Some services could offer to optimize your day, your schedule, but that's extremely private data. Location data. Well, sometimes I want people to know where I am, sometimes I don't. Of course, there's many, many other types of data that you could consider here and that are used by all types of and all kinds of apps and services. So, are you okay sharing this data with service providers? And in what situations? This is not a simple question. It depends. And what are the options? So, typically, you have two options. One of them is you share everything and you get the service, or you share nothing and you don't get the service, but now you keep your privacy. But this is not really a fair choice. At Microsoft, what we've been thinking about is how could we do something better? That's why I wanted to introduce the technology called homomorphic encryption. Homomorphic encryption is a new kind of encryption technology. It's very different from familiar encryption like AES or RSA. In fact, homomorphic encryption allows you to compute on encrypted data. So for example, AES allows you to encrypt data and store it forever. But as soon as you want to do any operation on it, you have to remove that encryption and then you can compute on it. Homomorphic encryption allows you to compute on the data without a key. So let me show you what I mean with this little schematic. Here we have a user on the left-hand side and a cloud service on the right-hand side. The user has data, they choose a key and they encrypt their data. And they can store it in the cloud service. This is all standard. But because we have used homomorphic encryption here, we can actually compute on the encrypted data directly. If you have very good eyes, you can see that the color of the files has slightly changed, which is an indication of the data being changed somehow. So the idea is that on the right-hand side, the cloud performs a computation on the encrypted data. But as you can see, the result of the computation remains encrypted, and only the customer, only the client has the key. Now, the encrypted data can be sent back, and with the key, the encryption can be removed, and the result can be revealed to the client. Excellent. Well, now your next question would be then, how do I get this? How do I do this? And here's how. We have created and released a library called Microsoft Seal. So it's a homomorphic encryption library. It's a low-level library developed in C++17. It has .NET standard wrappers, and this has actually been developed since 2015, but only last year we open sourced it under an MIT license. And we're actively developing Seal today. The source code is available on GitHub, and you can download it from that URL. Here's a fun little picture of the core people involved in the project. Well, great. So if any of you have heard about homomorphic encryption before, odds are that you've heard things like it's very complicated, very mathematical, maybe hard to use, maybe very slow. This was probably true when you heard it, but with Microsoft Seal, we're trying to change the situation. So here we have a performance overhead graph, and actually homomorphic encryption is very new. It was only invented in 2009, and it was extremely slow at that time. And for the couple first years, it was absolutely extremely slow. As you can see, we're talking about 10 orders of magnitude performance hit, which is really, really, really slow. Since then, however, until today, 2019, the performance overhead has come down massively. And today, we're looking at FPGA, GPU acceleration to this technology, and we expect further significant improvements in the performance. Usability, ease of use is another thing. Homomorphic encryption doesn't have to be difficult to use. I believe we can make it easy, and I believe we can make it accessible to normal developers, to people who are not mathematicians and not necessarily cryptography experts. This is what we're trying to do with Microsoft Seal. As one example of the practicality of this technology, we wanted to show you some kind of demonstration. And we chose to do a fitness tracker. Why a fitness tracker? It's because fitness trackers typically have some significant privacy issues with them. Because how do these apps work? They record your location. Maybe they record other health information about you. They store it in a cloud service. And at some later time, you can look at summary statistics or some kinds of predictions on your phone. But all of this data is actually stored in some cloud service. Well, this may not be what you want. That's why we decided that, well, let's try to implement our own private fitness tracker, which encrypts your location data, sends the encrypted data to Azure, stores it there in encrypted form. And whenever you ask, oh, how much did I run on this and this day, the computation, the summary statistics, some kinds of run classifications are done on the encrypted data in the cloud, and your phone only gets the encrypted result, which it can decrypt. Your phone only ever has the key. You can, in fact, try this yourself. You can come visit our booth, the Responsibly AI booth, and we're hoping to release the source code very shortly. Of course, I can talk about this, but it's another thing to see it in action. On the left-hand side there, you can see the fitness tracker. This is some Android emulator running it. And it's simulating a run. But as you can see, for all practical purposes, this is a fitness tracker. There's nothing special in it in some sense. From the user's point of view, you don't see that this uses homomorphic encryption under the hood. However, on the right-hand side, we see Azure's view of it. This is the database. And, well, it's not rendering those characters very well because it's encrypted binary data. So it's very small, but it says location, time, run route in those columns. But it's all encrypted. And Azure never sees this data. Only the phone sees the data. So now go download Seal, go try it out. It's all public. You can even do pull requests. And I hope that you visit our booth.
Thank you, Kim. So I'm guessing that all of you can understand a little bit when I was explaining to you that for me this is magic. How can you compute unencrypted data? It's mind-blowing, at least for me. I mean, it's like, I love the way that Kim explained it to me before. He said, it's like encryption is like a black box. You put your data in a box and you send the box to a container, right? But actually, homomorphic encryption is the ability to the box, to touch the box and do things with them and get something different out of that, but without ever seeing what's in the box. That's really amazing. And I'm going to brag a little bit on his behalf, because you didn't brag too much. So I'm going to brag a little bit on his behalf, and I'm going to tell you that this team, the team that Kim Line is part of, were the first ones that proved that homomorphic encryption was actually something that you could do on deep neural nets. That was an amazing breakthrough. So this research is really, really advanced, and I encourage you all to read the papers, experience Seal, and come to our booth, of course. And now we're moving to intelligibility, which is a really important thing in machine learning. Understanding how a model is behaving is fundamental to trust, right? And Harsh is going to tell you a very beautiful story that's actually grounded in truth. So it's the story of how the researcher understood this problem and devoted the next 20 years to solve it. So I really hope that you will experience this part of the presentation as personal as it is. And I'm introducing you Harsh Anori, data scientist.
That was, yeah, I planned that. I have a request for you guys. There are some kind of code snippets and demos, so if you are interested in being able to read those, please take a minute to try to come up. I realize it might be a little hard. There's always a tricky balance between showing you guys real code and glossy slides, right? So yeah. If everyone could like come up a little bit and fill kind of some of the empty seats, just if you want to see the code snippets, that'd be awesome. And yeah, this presentation will be a story that one of my teammates worked on several years ago, and then some real code with some real tools that we built to help solve these problems. So I'll start with the story. I've got some good news and some bad news. The bad news is that you've all been diagnosed with pneumonia, and about 10% of you are going to die. But the good news is that years ago, we trained a deep neural net to predict which of you are likely to die and which of you are likely to live, so that we can give you the appropriate treatment. If you're at incredibly high risk of death, you have to go to a hospital immediately. But if you're at low risk, the recommended treatment is to go home, take some antibiotics, drink some warm soup, and call us if you're not feeling better in a couple days. And that neural net that we trained turns out to be the most accurate model we could train on this data set. We worked with a team of doctors to collect this data. We tested out a couple configurations, and this neural net outperformed everything else. But there is more bad news. The neural net is a black box. We don't really understand it, and we don't understand how it's making its decisions. So we're afraid to use it on real patients. And I'll tell you a little bit about why. When we looked into the neural net, we discovered something interesting. Somehow the neural net learned that having asthma was good for you. That somehow having asthma, another respiratory illness, reduced your risk of dying from pneumonia. And this didn't sound right to us, and it didn't sound right to the doctors we were working with, who immediately told us that asthma is terrible for you if you have pneumonia. It increases your risk, and there's something wrong with the model. We have to go fix it. But the doctors told us something else. They had an explanation for why the neural net might have learned this pattern. You see, if you're an asthmatic, you're going to notice problems with your breathing almost immediately. And you have a doctor you can call when your inhaler might not be working in solving that problem. They're going to recommend you go get checked out. And when you get to the hospital and they find out that you have pneumonia and asthma, they're going to give you very high quality care very quickly. So in fact, asthma is not good for you. Asthma is terrible for you. But in this model, it's acting as a proxy for getting high-quality care, getting diagnosed quickly, and noticing your symptoms early, all of which genuinely do reduce your risk. It's not a problem with the model. The model is just learning statistical relationships in the data. But it is a problem with the data set. And it took a lot of effort for us to be able to discover this using interpretability techniques. So that brings us to this age-old trade-off. We can get great accuracy using modern machine learning techniques like boosted trees and neural nets, but it's been hard to get that level of accuracy with intelligibility, with the ability to understand how the model's making its decisions. And in fact, this has kind of been in the minds of every data scientist, that there's a class of models that are really high accuracy, like boosted trees, random forests, and neural nets, but that aren't very intelligible. And on the other end of the spectrum, we've got models like logistic regression and decision lists that are highly interpretable, but they just haven't been able to match the accuracy of these more powerful models. So in Microsoft Research, we've been thinking about this for a number of years, and today we're releasing an open source package with a brand new learning method that we're calling the explainable boosting machine. The EBM, explainable boosting machine, combines the power of modern machine learning techniques like gradient boosting and bagging, but it constrains them in a way to keep them really interpretable, like a simpler model like logistic regression. So there's two things we're claiming here. We're claiming we've got great performance and that we've got interpretability. We'll talk about the performance one first. If you're in the back, you might not be able to see these numbers, but we ran the EBM on a wide variety of data sets across a wide variety of domains. Other medical problems, financial problems, even business problems like churn. And we find that the EBM is competitive. We were up there with XGBoost and random forests, so-called state-of-the-art models of today. But what's more interesting for us is how we get this accuracy while staying completely interpretable. And for that, I'm going to switch to a Jupyter notebook to show you some real code and how this model works. So I think I got to configure this a little. Switching machines. All right. OK, great. So all I've got here is a Jupyter notebook. It's an interactive Python environment. And all I'm doing up here is loading in that same pneumonia medical data set that we talked about earlier and setting up a standard machine learning experiment, splitting the data into a training set and a testing set. And then now we're getting to kind of the more interesting part. With just 2 lines of code, I'm going to train the explainable boosting machine. If you guys have ever used scikit-learn in Python, it's the exact same API. So training a model there and training our model are exactly equivalent. But what gets interesting is what happens after we've trained this model. With the explainable boosting machine, you not only get a powerful predictive model, you can see exactly what the model learns, feature by feature, and really understand how it's making its decisions and how it works. So we have an interactive Jupyter notebook experience. I'm going to zoom out a little bit. That shows these kind of interactive plots to help you dive into this model and understand how it's working. And it might be a bit hard to see, but the first thing we see is kind of this ranking of features. What features did this model find important overall? We see things like your blood pressure was probably important in your risk for pneumonia, your respiration rate, and what it found most important was your age. So now that we know that, since it's the most important feature, we can dive into it a little bit and see exactly what this model learned for this feature. So this top graph here is what the model learned. The x-axis is your age, and the y-axis is what the model thinks your risk is. And immediately we start to see some interesting things. Your risk seems to stay low and flat from the ages of about 20 all the way up to 50 or so. And this makes sense, and it made sense to the doctors we were working with. Your risk really doesn't change that much if you're a 33-year-old or a 25-year-old. After about 50, your risk starts to climb steadily until about 85. And then again, at 85, it tapers off and stays flat until about 100. And then we see something interesting. Somehow the model thinks that your risk reduces after you're 100, that somehow a 102-year-old is at lower risk than a 95-year-old. And that doesn't make sense. So we asked our doctors, and they had an explanation for us again. The doctor said that it's pretty rare for someone who's over 100 to come into the hospital. And when they do, and we find out that the only illness they have is pneumonia, a treatable illness, there's a kind of human motivation to push it. Let's give them the most aggressive treatment we can. I mean, we're working with a centenarian here. Let's try to help them set the record. So we think that the drop at 100 is actually a social factor. Like 100 doesn't mean anything to our bodies, but it does mean something to us as humans. It's a nice round number. And these types of effects get coded in the historic data that we collected, and of course get coded in the models that we see. So this is what the EBM learned, but it might be interesting to compare this to another interpretable model that you might be more familiar with, and we can really look at the differences. So we're going to turn to the gold standard of interpretability, logistic regression, and we're going to look at what the differences are between what the EBM learns and what the logistic regression learns. So on the right is that same EBM graph, just squished a bit, and on the left is the logistic regression. And almost immediately you can see the differences. The logistic regression is a very constrained model. It's only allowed to learn a single line for every feature. So it thinks that risk is uniformly increasing as your years grow. The difference between being 40 and 20 is the exact same as the difference between 80 and 60. And because of that, it's not expressive enough to capture the real patterns in the data set. I mean, when we talked to the doctors, they agreed with us that your risk should stay flat between 20 and 50. There's really no physiological difference. So picking the right model for the job can make a very big difference in how accurate your models can get. And so the next question is exactly that, accuracy. I mean, it's great if we have a highly interpretable model, but if it does a terrible job at predicting, it's not really good for anyone. So to check out the accuracy, we're going to compare the EBM, the logistic regression, and we decided to throw a black box model in there too. We're going to train a random forest with 1,000 trees in it and see what kind of performance we can eke out of that forest. In here, we've got a dashboard experience. It's a little constrained in the notebook, so I'm just going to pop it into a new tab so we can look at it. But all of this code is running locally on this device. It's all hosted on localhost. It's not talking to any servers or anything. It's just a nice visualization platform. And when we look at the model performance, these are ROC curves, so a standard machine learning metric for classification problems. We see that, as you might expect, the black box model outperforms the logistic regression. But surprisingly, in this data set, the EBM outperforms the black box that we can throw at it too. So we've got a model that's highly interpretable, it's flexible enough to represent the data well, and it's getting great performance. And we can look into this model overall and see exactly what it's learning and make adjustments when we see things that are problematic. But the last question always becomes, what if this model makes a prediction about me? What if the model tells me that I'm really high risk? what are the factors that mattered in my prediction? I don't want to look at what the model's learning overall. I want to know exactly why it thinks that I'm high or low risk. So in this tool, we're also including what we call local interpretability, where you can see exactly how an individual decision is made and break it down. So we're going to take a look at the EBM, and we picked an interesting person out of this data set to dive deep into. What you're seeing here is a breakdown of the important features in this person's prediction. If the bar is orange and to the right, it means it's increasing their risk. And if it's blue and to the left, it's decreasing their risk. So this person got a prediction probability of death of about 40%, which is pretty high. But it turns out they actually did pass away as a result of pneumonia. So the real prediction, you could say it should have been a 1.0. So now the question is, why didn't the model predict even higher risk? So the factors that are increasing risk seem to make sense for us. Their blood pressure is abnormal, their age is 90. All of these really should be pushing risk up. But when we look at the factors that are pulling that risk score back down, we see, as you might expect, asthma. This person had asthma, and it pulled their risk prediction down because of those artifacts in the data set that we talked about. In fact, there's only one feature that's even lower risk than asthma. And it might be hard to see here, but it's a history of chest pain, which is even more surprising to us. But the explanation is very similar to the asthma story. If you have a history of chest pain, and you notice something wrong with your chest, I mean, you might think you're having a heart attack. You're going to get to the ER immediately. You're going to be able to cut lines, and you're going to get the most high-quality care possible. So just like the asthma case, and just like the age being over 100, this history of chest pain is a flaw in the data set that's encoded in the data. But with interpretable models, we can see those flaws and do something about them. So I'm going to switch back to the PowerPoint. It's going to do a magic transition. One thing I want to really stress is every single data set we've ever looked at has these flaws. It's not just high-risk medical situations or loan approvals in banks, although we have looked at those. But even bog-standard business problems have these data sets. We found flaws with the way we do churn modeling. We found flaws with how we draw reliability curves. Every single data set has these artifacts, and I guarantee that your data sets have them too. But now that we have interpretable modeling, that's OK. We can find these flaws, we can adjust for them, and we can build more robust models as a result. So we're releasing a tool today called InterpretML. It's on GitHub, and I'm going to tell you a little bit about what we're including in there. The first component is this idea of glass box models. These are models designed for interpretability. It includes the explainable boosting machine, but also models like linear models, decision trees, and rule lists, so you can compare them and find the ones that work best for your needs. On the other hand, we know that sometimes you've got a black box model already that you want to try to explain, maybe tease some explanations out of it. And for that, we're including a suite of popular tools to help you open up the black box. Tools like partial dependence plots, sensitivity analysis, LIME, and SHAP. All of these tools are being combined and released in a package called InterpretML. We just got on our GitHub today, so we're really excited. We're hoping you guys go check it out. It comes with this nice unified API for all of these different methods. So if you train one of these, you can train all of them. It comes with those nice interactive visualizations that we talked about earlier. And we've got a small but really eager and active development team working on making this thing better and better. So please give it a try. Check out our GitHub, and please give us your feedback. We really want to work with you all and see how we can make interpretability available for everyone. And with that, I'm turning it back to Esther. Thanks.
Session. I'm assuming that you probably have a lot of questions. So the way to do questions in this session is to come up to the mic, which I know can be intimidating, but stand up and ask your questions, because if you don't, I'm going to start asking mine. And as I said before, I can speak for days, so you don't want me to do that. So think about your questions, and while you're thinking about them, I'm going to introduce you to Scott Hugerberg. Scott is one of the engineering leaders at Microsoft that's looking at how he's looking at a lot of things. So he's looking at how to scale this kind of technologies across all of our engineering practices, and not only this. So the way that I spoke before about the complexity of all these responsible AI considerations, Scott is really thinking hard about this whole life cycle and how can we improve our engineering processes. So any question that you have on the topic, Scott will probably be able to answer. No pressure, Scott. And and I will handle my microphone to him. So please come by and ask your questions. And great, we have questions, so I won't start with mine then.
First thing I'm going to do is I'm going to have the other experts come up, so we're all ready up here. Great, let's start it off.
Yeah, hi. I have a question, actually, Scott. I've seen in your title, Ethics and Society. I'm curious about your take on, we're very close to getting autonomous self-driving cars. Mm-hmm. There are numerous examples where an autonomous car probably determines that it will run into a crash situation and has the choice between killing the driver or killing 5 other innocent bystanders or so. How do you build these types of ethical questions into AI and autonomous systems?
Great question, and something that gets brought up a lot in our field, as everyone in this room is probably super aware. There's no clear answer, and so what we've developed, I think that our approach is to get at that nuance, because it's a very nuanced question, right? It ends up not being an if statement, if baby, break, if not baby, do something else. It's really about understanding how the overall system works. And so, I won't go into too much detail, but how we think about it here is the first thing we do is we say, hey, we have these ethical principles at Microsoft, and how are we going to bring those into the engineering cycle at all levels? Because the autonomous car is one example, but there's also the question that Harsha brought up, right? Which is, should we deploy this model that we don't know how it works, in a healthcare situation, which could impact your healthcare? And so the first thing we want to do is, at a broad level, understand how these things are making decisions, and then kind of make the call on where we put them and how we use them. And so at Microsoft, that really comes down to all of our ethical principles, and then the next layer down is how we bring those into the engineering cycle through best practices, the tools that we've talked about here, and different approaches. Does that answer it?
It's a complex question.
Yeah, super complex. I think the challenge is we don't, I guess maybe to answer more directly, what I don't want, at least teams at Microsoft, to do is get caught up in these theoretical, really tough conversations. What I want them to do is think really hard about how the software they're building is going to be used and how they mitigate that and tailor that as much as they can, using all these different approaches. And so whether it's an autonomous car team, whether it's a healthcare team, or it's just someone in an office that's trying to build an intelligent service, that they are laser focused on who they're trying to solve and solve it the best way.
Hi, I have 2 specific questions. First, I believe your name's Kim, on homomorphic. So one of the main applications often is multi-tenant data, right? So you might have multiple customers, each who would like to have ownership of their data, but you would like to aggregate all the data across your customers and train a model together. Is that possible with homomorphic encryption?
It's possible. So is this on? Most homomorphic encryption schemes are like single key, meaning that there is one party that sets the secret key and the public key. So these are public key encryption schemes. But there is one secret key, one party that can decrypt. There are some multi-key systems too, where multiple parties can kind of share the responsibility of decrypting. It is possible to set up collaborative scenarios where for example, multiple parties use a shared public key to encrypt their data and store it in some kind of cloud service and do then some kind of computation on this together. Maybe it's some analytics or something. It gives an encrypted result, which then can be decrypted using the secret key. And well, maybe one of those parties holds the secret key. Maybe it's some kind of external party that holds the secret key and can reveal the result.
So maybe I'll just give an example. So let's say I'm a company that does machine learning, and then I've got two clients, client A, client B. Client A has their data. They have their own secret key. They send their data encrypted to us. They would like to have assurances that their data is not legible to anyone else ever. Client B, same thing. They want their data to be only legible to them. Is it possible to do operations on their data together?
Right. So it is not in using most of the homomorphic encryption schemes, because in this particular scenario that you describe, you kind of want two data owners, two different secret keys, and you can't cooperate like across different types of encryptions, because who is supposed to be able to decrypt the result, right?
Right.
But like I said, there is some very recent research on multi-key homomorphic encryption, which seems like it can be possible.
Okay.
But so currently Microsoft Seal does not have such a multi-key functionality.
So perhaps in the future there might be some scheme by which it's...
I think it's possible. Yeah, I mean, I know it's possible.
Okay. And then, if you don't mind, a second question really for Interpret ML.
Sure.
So, pretty simple. It's MIT license, is that correct?
Yeah, MIT licensed, all on GitHub, all our developments out in the open.
Okay, great. Just a quick comment would be, it's pretty amazing, and I'm pretty sure I'm going to use it probably within this month.
That's awesome, yeah.
I was wondering so you mentioned a few models that are under that glass box schema. What's the roadmap for future models? What are you guys thinking in terms of growing this library?
Yeah, so we're a team out of research, and so we want to stay plugged into what's happening in research conferences and kind of provide reference research implementations of new work. I know that there is a lot of active work in the future on kind of building more reliable if-then rule systems. So some people have empirically shown that you can get decent classification results by learning a set of really human interpretable rules, like if these three conditions are true, then predict this, otherwise predict this. And I think that's an area of interest for us, so we're looking a lot more into trying to build out better rule systems, but it's really about where the research goes. On our side, we're trying to continue to improve EBM as well, of course, and make it even more robust.
Awesome. Maybe if can I just add to that too, just to give a little bit of context too. So, I think there's no product announcements today. Make sure I still have a job tomorrow. But you can imagine Microsoft all up. This is a significant priority, and so Harsha talked about tabular data sets. You can imagine visual data sets and speech data sets are another focus, and so I think you will continue to see kind of a constant release of iterations on things we've already released and new types of data sets and models in kind of the interpretability space.
Yeah, I think that's fair. It's not exactly like Scott said. And right now, Interpret ML, to be clear, focuses a lot on tabular structured data sets. So that's where we're putting our first effort.
Awesome. Thank you.
Hey, good evening, guys. This is Barney from Ernst & Young. And Esther, I think this is one of the most lively sessions I've seen since morning, and thanks for that. Very interesting. Thanks for EBM, because I can truly see how easy it's going to make the job of the data scientist in terms of explaining things, which has always been traditionally difficult. The question that I have is that Microsoft as an organization, beyond enabling technology, has a larger role, which is the ethics conversation that we are even having today. Are you guys partnering outside of the institutions, any with government organizations or EU or any national regulatory agencies in terms of putting this in a more formal standard, like BCBS, CCAR for the financial reporting? Is there anything that you guys are doing outside of the technology spectrum in terms of regulatory standards?
We are. I won't try to list them all out, but I will tell you both Satya, our CEO, and Brad Smith, who's our president and chief legal officer, spend a ton of time, not only with industry groups, like you'll see as part of like Partnership for AI and a bunch of these groups, but also just general regulation across the world, because I think we think it's super important we get this right. And we also believe that it can't just be talk. Like there's lots of folks talking and about this types of regulation, and there's lots of principles, and we love our principles. But our job, like the folks on this stage, is to make that real. You know, what does transparency mean for the data scientists building the model? And so we have a really tight relationship with those bodies to say, we've proven this out at Microsoft in a product. Now, like, this should give it more credence to be part of like a regulation or a best practice. So I think that is top of mind for us and will continue to be.
Very impressive. Thanks, guys. Appreciate it. Cheers.
Thank you.
Hi, great session. I really appreciated it. I was curious, though, given the framing of the session, why you didn't talk about bias?
Time. I wish I had a better answer, but it really is that. I mean, we were talking as we were planning this session. We were like, where do we start? We should just have our own conference because there are conferences on this, you know.
I would second that. Go ahead.
Yeah, I mean, and so bias. I mean, we put bias in our fairness principle. We focused every day on reducing things like bias in our data sets and our model decisions. So we didn't touch on it here. With that said, the examples that Harsha gave are, you know, kind of this profound example of bias and how dangerous bias can be when you don't understand it. We actually don't use the term bias anymore. We use fairness because it's kind of funny. Actually, probabilistic systems, you're trying to create something actually extremely biased. You just want to know where it's biased. And the best systems are just really biased in a way that makes sense. And so anyway, that's a long way of saying we didn't have time to go into it deeper, but it's a huge focus area for us.
To let you know that we are hosting a session on facial recognition challenges, and a huge challenge of facial recognition is bias, and that session will be tomorrow, Tuesday at 8:30 a.m. So awesome. So go there, because Jacqueline Krones is driving that session, and it's really mind-blowing. So definitely go to that session. We will be talking specifically about facial recognition, but it's the approach is extrapolable to other things that we are thinking about.
Thank you.
Thank you.
Hi, I will repeat what was said before, that the session was really great. And I have a little bit technical question about this explainable boosted machine model, especially the variables importance measure. How it works compared, for example, to the existing measures that exist for random forests or boosted trees, like the mean decrease of Gini index?
Sure. You could hear me, right? Yeah. Yeah, it's a good question. I think the way I like to think about it is importance measures based on like information gain or Gini criteria or any of these things are effectively heuristics, right? Like you're effectively trying to rank things in a list, and so you're looking at things like how much information do I gain by splitting on this criteria? But there's an excellent paper by a student at University of Washington, Scott Lundberg, who talks about how lots of tree-based interpretation methods are inconsistent. Like heuristics can fail in multiple ways, and so I think a lot of those, I would really refer you to Scott's paper on how attribution can be kind of inconsistent, how he creates these amazing experiments where he grows two almost identical trees and forces one to have a more important feature than the other, and shows how all those attribution metrics can fail. With the explainable boosting machine, our kind of like the zoom into each feature is exactly what the model learned, right? So it is not a heuristic, it is not a guess about how the model's performing like a partial dependence plot might be. It is exactly what it learned because we constrained it in a way that forces it to represent the data that way. So I guess the difference is kind of exact interpretability versus approximate interpretability, right? And I think with EBM you get exact, with other attribution methods you're getting approximate. That makes sense.
Thank you. And another question, but this time about the interpretability of the local prediction. You showed this example where the risk for the patient actually was very high, but model predicted the value predicted by the model was quite low, and thus the library and the model has ability to calculate something like in the linear regression setting is called these prediction intervals or versus confidence intervals which are calculated for the whole data set, whole population, bearing in mind.
Sorry, could you repeat that last part?
Okay, I mean this for this value in case of a single prediction, is it interpreted? Is there something calculated for it, like some values like prediction intervals in the case of linear regression?
Right now, not exactly. I think that's still kind of an open area of research.
Because what I thought was in this world of linear regression, we have this confidence interval versus prediction interval, where about when we speak about confidence interval, when we interpret the expected value of the predictive variable,
right,
versus the exact value, the value of the variable itself, which of course have to also include the variance of the variable itself, not also this irreducible error.
Yeah, so there's an idea of kind of error bars on each individual feature that we learn, but kind of how to aggregate those and display it in the right user-friendly way for like each local prediction is still something that we're like thinking about. But it's an excellent question. It's something that's definitely been on our minds.
Thank you, Matt.
Yeah, very. Thank you for the question.
Microsoft has O2ML package.
Well, I'm sorry, what was that?
So Microsoft has the O2ML package, where it will check which model will fits the best. Is EBM going to be part of the list of models that it goes through?
We don't have like product announcements yet, but we're just a small team in research, so I think that's the best.
The thing, the answer, the public answer I'll give you is nothing to announce today, but again, this is an area of focus for the company. You will see, I think you will, you can have confidence, you will continue to see a bunch of these types of tools start being released, whether it's an AutoML or just kind of our overall, Azure AI story. I think you'll stay tuned.
Just wanted to ask, any thoughts on what interpretability might look like for things like image or sound classifiers?
Yeah, it's a great question and something that I think is another focus area for us. And there are some approaches like Lime, that Harsha touched on. The key is it's the human interpretability, is the human understanding, which sounds like you're well aware of. And so I think some of the approaches we're most interested in are how do we help you understand classes, of errors, and then maybe drill all the way down in a way that allows a human to maybe understand it. So for example, if you're building a facial recognition system, how do we help you understand that maybe a thicker rim glass or a thin rim glass is actually your problem with your accuracy? And so I think, and then the same thing with speech. What is it? Is it a certain type of accent or a certain type of speed? All those types of things. I think building tools that spit out more than just this is the XY coordinate of the pixel that failed in your neural net, and actually saying, no, this is the area of the picture, or this is the section of the speech, I think is an area that we're focused on.
Thanks.
I guess something that's loud. Something I was thinking about, you said with the EBM, you can see exactly what was going on. And the asthma and the chest pain were indicators, obviously wrong, but should you change those? Because they correlate with the data and presumably with what is going to happen in the future. If you're trying to model, an outbreak of pneumonia or anything like that, would you want to change that?
It's a great question, right? Like I think it really depends on your setting. So in this setting, this model was going to be used to score future people coming in and deciding whether or not they get the right treatment. And so in that case, we do want to change it. We don't want to penalize someone fresh coming in just because they're an asthmatic. Like the historic data has the effect of their treatment already kind of built into the label, but we don't want to deny asthmatics en masse, right? But you could make the argument that maybe if you're an insurance company trying to decide these things, that you should leave it in there because that's kind of an artifact of the real human process, right? So I think it's really situation dependent. I think what we really like is that these models are editable and you can visually see what edits you're making and exactly how it'll affect the model. So the power to edit these things after they've been trained without having to go add a bunch of synthetic data and try to tune your models with a bunch of hyperparameters, like giving you the power to do that is kind of the first step, right? And then whether or not you do it is highly situation dependent. I'll touch on one more example. One thing that we sometimes have done in the past is train a model that includes features like race or gender, right? And because the data has bias in it, the model will learn that bias too. But you can see exactly what bias it learned and then zero the differences out before you deploy it, right? So sometimes it's, like I think the worst thing you can do is kind of hide the features from the model, like drop gender or drop race, and let that effect be hidden in all the other features in your data set through correlation. The best thing you can do sometimes is let these models learn the bias, right? And with editable models, you can see where that bias is and zero it out. So that's another case of where we like to try to edit these things before we deploy them.
I guess it kind of is the same question again, but in that case, you're removing race or something like that out of there. I know in a lot of medical cases, like spontaneous pneumothorax, it pretty much exclusively affects really tall white males. So if you did edit that bias out of there, you're all of a sudden you're looking, is it anyone on the basketball team? Because it's not going to happen. It's almost 0% outside of the really tall white male demographic.
For sure, for sure. And in that case, maybe you don't want to do it, right? Like, I think you're exactly right. Like, there are situations where you absolutely don't want to, and there are situations where you absolutely should. And it's kind of your job as a scientist to sit there and parse through these things, right? Like, so it sounds like you've got a really good handle on it.
And just to add that at a global level, I think everything's gray with these probabilistic systems, and they're so scenario specific. And so what you're seeing, kind of us do is say the first step is just understand what's happening. And then the person building the system can make the call. And hopefully one day we'll move beyond that, where we'll be able to answer these questions ahead of time or in some sort of automated way. But I think step one is just how do we even understand how these neural nets and all these things are making decisions, which is a tough one to figure out right now.
Awesome. Thank you.
Hi. So I just had a quick question about the EVM. Everything that you showed was one factor in how that related to the overall result.
Mm-hmm.
If there's an instance in which case A by itself is fine and B by itself is fine, but A and B together are a big indicator of something, does EBM have a way of dealing with that, or is that something that's still in the
Yeah, it's a good question. We didn't touch on it for the sake of time, but one thing the EBM does is detect what pairwise interactions are significant in the data set and learns those as features as well. So you're right that interactions make a big difference in certain data sets. So we, as part of the tool, do learn those interactions and do visualize them in just a slightly different way than we do those one feature at a time. And we find that in some data sets it makes all the difference, right? So spot on question.
Thank you.
So I wanted to wait a tasteful interval before coming back again. But I really... But I wanted to kind of follow up with, I think, what someone else said about sort of probabilistic, in terms of interpretability. It would be nice to get some sort of, I think he said variance on various factors and that sort of thing, which directly ties in with some of the later questions, I think, too. And so what's the roadmap for that specifically? I think for me, for at least the application that I'm most interested in, and gets into responsible AI is, I think a lot of times the responsible thing to say is, I don't know. And so having really good metrics around that, and like how certain are you of your result, would be very, very beneficial, especially for a business-to-business product.
Makes perfect sense.
I mean, no product announcements, just know we're very committed. And that's what I can say. But I'll tell you, the way we look at, maybe just the way to frame this space is how we talk to product teams is really just not in terms of responsible AI. We talk to them in terms of quality, right? You'll hear, if you talk to a product team that says, oh, I talked to Scott, they're like, oh, he gave me the speech. But it really is, we have decades of research and processes and tools around deterministic systems, right? QA processes. We are at the start of that for probabilistic. And so all of these types of approaches that we're inventing are new. And so I think your question is great. And so I think the way to say this is in 30 years, I think you'll say, oh, Microsoft has this incredible suite of QA processes and best practices and tools, just like they do for deterministic systems. At the same time, we're also trying to deliver this message is if you don't know what it's doing, if you don't know what your neural network is making a decision, and it could be punishing an asthmatic or whatever, then probably shouldn't be deployed. And so that's kind of how we look at the overall problem.
Yep. And specific, so yeah, actually, let's just make it, is there an opportunity later in this conference to discuss this and other more technical problems?
Yeah, for sure. Sam's back there. He's been working with me on this project. We're both going to be at the booth, the Responsible AI booth, for the rest of the day today and all day tomorrow, too. So, yeah, I think that's probably the right venue for us to go into a bit more detail.
And we'll be here for a little bit, too, if you want to grab us.
And I'm the timekeeper. So thank you all for all the great Q&A. Thank you very much. It's been great. And we hope to see you at the booth. And can you pass one slide? Can you show the next slide? As a summary of everything that we discussed, here are all the links to everything that was shared today for you to recap. And anything else will be at the booth. So again, thank you very much. You've been great. I hope you liked the session. Thank you. Have a great build.